Hi guys, it's Daniel here, and it's our favorite time of the year again, Olympiad prep time. So let's begin prepping for Olympiads. This is gonna be IMO Shortlist 2002 Geometry Problem Number 2. So let's first do the problem. Let ABC be a triangle for which there exists an interior point F, such that AFB is equal to BFC equals to CFA. Let the lines BF and CF meet the sides AC and AB at D and E respectively, and we want to prove this inequality. So the first thing that catches our eye is, of course, this condition. This angle AFB equals angle BFC equals angle CFA condition. And for those of you who are knowledgeable about some geometry trivia, this point F is called the first Fermat point. And that will actually help us immensely in solving this problem. But I'll just prove this problem without using any of that knowledge. For those who don't actually know the properties of the first Fermat point. If you don't know, you should search it up, definitely. And I'll also talk about some of it in this video right now. But yeah, knowing some geometry trivia can be very useful. And second of all, our second thing that we notice is we want to prove this inequality, which usually means that we're going to have to use some algebra. But actually, I found a solution without any algebra, which is nice, and I'll show it to you right now. Completely 100% synthetic, just the way everybody likes it. Alright, so let's take a look at this diagram here. I already drew the diagram so far that we've read. And of course, since angle AFB equals angle BFC equals angle CFA, we know that these are all equal to 120 degrees, since they add up to 360 degrees. And yes, marked like this. And also, since the diagram is kind of not symmetric because we don't extend AF, let's extend AF as well, just to make it symmetric, even if it's not really useful. So second thing we notice is that if we have three lines here that each are 120 degrees, then if we extend the lines, then each of the angles now are just going to be 60 degrees. All of these are 60. 60, 60, 60, so on and so forth. Alright, so now if we know that each of these are 60, then we have this very curious property that if we draw this circumcircle right here, the circumcircle right here, then first off, since angle AFC is 120 degrees, it implies that if we extend FD to hit it right here at, let's say, D prime, then that means this arc, this angle ADC is going to be 180 minus 120, which is 60 degrees. So this is 60 degrees. Furthermore, since each of these angles are 60 degrees, if for example D prime FC is 60 degrees, then we know that this is 60 degrees. And since we know that angle AFD prime is 60 degrees, we know that this is 60 degrees. So in fact, we know that ACD prime is an equilateral triangle. So, and this is one of the properties that you would know immediately if you knew the Fermat point, the first Fermat point, since in fact, if we draw this thing for the other two sides as well, let's see, keep on drawing, draw this equilateral triangle, and then if we draw the third one as well, another definition, as you can see, of the first Fermat point is the intersection point, the concurrency point of B to D prime, C to E prime, and A to F prime, where E prime, D prime, F prime are the third vertices of equilateral triangles that are extended on each of the sides. But for this problem, this will be all we need, just these two triangles. Now we have that ED, we have this length ED, and we have the length AB and AC. Now, the nice thing about having equilateral triangles on the sides is that we have equal sides as well as equal angles. In particular, AB is equal to AE prime, AB is equal to AE prime, and AC is equal to AD prime. And why is this nice? Well, we see that AE prime and AD prime are pretty much they're pretty much on the same line. They're not actually on the same line. My diagram makes it look like they're on the same line, but AD prime E prime is just a really thin triangle. So this tells us that since we're dealing with inequalities here, and we have this AE prime, AD prime plus AE prime on the higher side, on the bigger side, that since we're given this really, really thin triangle, it's probably a good idea to apply the triangle inequality here. So in this case, this thing is greater than or equal to D prime E prime. Like so. So now, all we need to do now is prove that D prime E prime is greater than or equal to 4DE. And this is a much nicer statement because D prime E prime, well, D prime and D are both on the line BF, and E and E prime are both on the line CF. So we can probably find some sort of geometric way to relate between the two. And the first thing that comes to mind is we can take a homothety. That is, if we take a homothety with center F, sending line DE to something that's 4 times its original size, so a homothety of ratio 4, then it gets sent to something like, alright, D prime gets sent to something like D double prime, and E gets sent to something like E double prime. And then now we have this line D double prime, E double prime, that is 4 times the length of DE. And now all I need to do is prove that D prime E prime is greater than or equal to D double prime E double prime. So in order to prove this, first thing we need to do is, well, if we take a look at the triangle FE or FD prime E prime, clearly since this is 120 degrees, it is a obtuse angle. So in order for D double prime E double prime to be less than D prime E prime, it'd be very nice if D double prime E double prime is contained entirely within this triangle, because if that is true, then obviously it's going to be less than or equal to D prime E prime. So that's what we're going to set out to try to prove, that D double prime is between D prime and F, and E double prime is between E prime and F. So since these two are just dealing with that section of the diagonal, let's just redraw that section. So we have a equilateral triangle. Here's D prime. Here's D. Here's F. A, C. And we want to prove that D double prime, that is, if we take a homothety sending D to D double prime of scale 4, that we want to prove D double prime is less than or equal to D prime. In other words, we want to prove that D prime is greater than or equal to 4 times DF. Like so. So how exactly do we prove this? Well, we have an equilateral triangle here, so the first thing you might notice is that if we draw this line right here, this line, and let's say D star and F star, this line actually represents an equality case, right? Because we can easily see that, well, it's just some length chasing with equilateral triangles, that this thing D prime D star is 3 times the length of D star F star. So that means the homothety from F star takes D star exactly to D prime with scale factor 4. So this is the equality case. So maybe we can use this to prove the general inequality. Well, we notice that D prime is greater than or equal to D prime D star, because D prime D star is the height from D prime to side AC, and D prime to D is a hypotenuse. So now we need to prove that D prime D star is greater than or equal to 4 times DF. But we also have that DF is less than or equal to, or 4DF is less than or equal to 4 times D star F star. And the easiest way to see this is that d prime f star is greater than or equal to d prime f. Meanwhile, d prime d star is less than or equal to d prime d. So therefore, d star f star is greater than or equal to df. So now we have that, since this is an equality case, going around the inequality like this shows that it is true. So we finally have that d double prime is between d and d prime, and e double prime is between e and e prime. So that means that d prime e prime is greater than or equal to d double prime e double prime, which means that d prime e prime is greater than or equal to 4de, which means that ab plus ac is greater than or equal to 4de, and we are done. Hi guys, it's Daniel here, and today as a last minute AIME 2 prep, I'm going to try to solve, or not solve, I'm just going to try to explain as many AIME 1 problems as I can in 20 minutes.